friends, this is Priyanka. Today we are going to solve a problem on 4-bar chain for the velocity diagram and acceleration diagram. So while drawing these diagrams, the main important question is that in which direction we have to draw the velocity vector as well as radial and tangential components of acceleration. So you are going to learn the detailed explanation about the rules while deciding the directions. So please watch this video till end and make sure that you have to note these important rules in your notebook. And you can apply these rules on each and every question for the velocity diagram as well as acceleration diagram. So first I will read what is the given problem. PQRS is a 4-bar chain with link PS fixed. The lengths of links are PQ 62.5 mm, QR 175 mm, RS 112.5 mm and PS 200 mm. The crank PQ rotates at 10 radians per second clockwise. Draw the velocity and acceleration diagram when angle QPS is equal to 60 degree and Q and R lie on the same side of PS. Find the angular velocity and angular acceleration of the link QR and RS. So this was the given question. So as per the given data, we have to first draw the space diagram. So here the link PS is fixed and we have to consider some suitable scale. So for this fixed link PS, it is 200 mm. So we can say that 200 mm is equal to 20 cm. So here we will use scale 1:1. That means we will take here PS is equal to 20 cm. Now here is the crank PQ that is inclined at 60 degree, and what is the length of this PQ, that is 62.5 mm, that is equal to 6.25 cm. So at 60 degree angle we have to draw here this line PQ, which is of length 6.25 cm. Now how to locate the point R? So from this center Q we have to mark one arc for the distance 175 mm, that is 17.5 cm. So we will use here the compass. We will use here the Q as a center and mark here one arc for 17.5 cm. Now in the same way we will use here the S as a center, and what is the distance? R is given 112.5 mm, that is 11.25 cm. So we will take distance 11.25 cm and we will take here S as a center and we will mark here one arc. So here is the point of intersection. So if we join these 2 points, we will get QR and RS. And it is also given that the point R or these two links are on the same side of this fixed link PS. So here in this way this diagram is getting completed. Now what is the given data? So if we observe in the given data, the omega QP is given. So how we can define this? So omega is the angular velocity. So this angular velocity of this point Q with respect to point P. So here P point is fixed, S point is fixed. So we can write here omega QP is equal to 10 radians per second. So first we will draw the velocity diagram. So from this omega we can calculate the linear velocity. So how to calculate the linear velocity from omega? So we know that V is equal to R omega. So R is this distance PQ. So this distance PQ we have to take in meter. So we can write here as a distance in centimeter to meter. So how we can write here? That is 0.0625 meters. So we will take here VQ, that is VQP is equal to VQ because point P is fixed. So here omega is 10 and what is the distance PQ? That is 0.062 meter. So when we take this we will get the answer 0.625 meter per second. Now while drawing the velocity diagram, we have to first show this velocity QP in this diagram. So how to show that? So if we observe the question here, the rotation of this crank PQ is given in the clockwise direction. And we know that this linear velocity is in the perpendicular direction for this link PQ. So these two edges for the protractor are also perpendicular to each other. So I will align one edge with this link PQ and from the other edge I will draw one perpendicular line. Now in which direction we have to draw this line? So if we observe, the rotation is the clockwise rotation. So in that direction I will draw here perpendicular line passing through this point Q. So this is the line and we have to show arrow that is in the same direction of this rotation, and I will say this is the VQ. So if we observe, this is the magnitude and here is the direction for this velocity of Q. So now how to draw the velocity diagram? So for this magnitude we will decide some suitable scale. So I will take here for 1 meter per second is equal to 20 centimeter. So here what is the magnitude? 0.625 meter per second. So here is the question mark. So what is the scale that we have to take? So we will make here the cross multiplication, that is 0.625 multiplied by 20. So which is equal to 12.5 centimeter, and here divided by 1. So here it will become 12.5 centimeter. So if we observe here in this diagram or in this space diagram, there are two fixed points P and S. So while taking the velocity diagram, first I will locate the fixed point. That is, I will use small p and small s for the velocity diagram. Now magnitude is equal to 12.5 centimeter and direction is in this downward direction. So I will take this roller and I have to take this, or I have to transfer this line parallel to this VQ from the space diagram to the velocity diagram, and I will mark here 12.5 centimeter. So here initial point is P and final point is Q. So I will use here Q. I will show arrow also, and this vector PQ indicates the velocity of Q. So in this way I have shown this. Now we will move for the next. Now again from this point Q, here is the link QR that is getting attached. So how we can show this velocity? So we know that velocity is always in perpendicular direction for this link QR. So I will make here one line, that is this getting aligned with this one edge, and from the other edge I will draw, this is the perpendicular line. So now if I take parallel line to this construction line passing through this point Q, now I don't know in which direction I have to extend this. So for that I will just take the line parallel to this QR, that is construction line, and I will transfer this passing through this point Q. Now in both direction I will draw this. Now currently the direction is the unknown direction. Now location of point R, that is also unknown. Now we will move for the next link. So here is the link RS. So how we can show the velocity? So we know that the velocity is always in the perpendicular direction of the link. So again I will draw here one construction line, that is one perpendicular line to this. So this is the construction line, so we have to remove this after making parallel line. So now I will take this line parallel to this. Now here is the fixed point S. So for this link RS, we have to draw the velocity vector passing through this point S. So here it is already located as it is the fixed point. So I will draw the line parallel to this line passing through this point S. So if we observe, here is the point of intersection. So we can say that this point of intersection is the R. So here in the downward direction we have to remove these edges. Now we will give the arrow. For this RS, S is the fixed point. So I have to show arrow in this direction. Now this vector S to R indicates us the velocity of R with respect to S. So I will write that VRS. Then here is the initial point is Q and final point is R. So I will show arrow. So this link will indicate us the velocity of R with respect to Q, because initial point is Q and about this point Q, R is getting rotated. So here I will show velocity of R with respect to Q. Now I will show here the velocity in this space diagram. So how to show? So this is always perpendicular line. So this is the construction line, so I will extend this line. In the same way, this is also perpendicular line. So how to show for this line QR, that is the velocity. So for this QR, the velocity is in the upward direction. So make sure that here is the upward direction and this is the VRQ. Now for this link RS, so for this VRS, the direction is towards the right hand side direction. So here is the direction, so I will say that VRS and here is the VRQ. Now we will move for the calculation part. So here we have to find out what is the angular velocity for this link QR and this link RS. So how to find out that? So before that we have to first calculate what is the linear velocity for these links. So how to calculate the linear velocity? So velocity of RQ. So if I observe here, we have to measure this vector Q to R. So what is its length? So its length is 7 centimeter. So from this 7 centimeter, here is the scale. 1 meter per second is equal to 20 centimeter. So for 7 centimeter, we have to take 7 divided by 20. That is 0.35 meter per second. So here this is the velocity of R with respect to Q. And here I have shown the direction. So now we will calculate what is the angular velocity. So for this angular velocity, if we observe here, angular velocity of R with respect to Q, that is VRQ by length RQ. So for this length RQ, we have to take in meter. So 0.35 divided by 0.175, which is equal to 2 radians per second. Now we have to decide in which angle there is the rotation. So if we observe omega RQ means angular velocity of R with respect to Q. So suppose if we take Q as a center and move the compass in the direction of this velocity. So here this is the anti-clockwise direction. So I have to write the rotation is the anti-clockwise about Q. So I have to write answer 2 rad per second anti-clockwise about Q. About Q. Now we will move for the next. So next we have to find out the linear velocity of RS. So we will measure this vector S to R and its length is 7.5 centimeters. So as per this scale, 1 meter per second is 20 centimeters. So for 7.5 centimeter it is 0.375 meter per second. So now we will find out the omega. So omega RS is equal to VRS divided by length RS. So length is we have to take in meter, that is 0.375 divided by 0.1125. So if we calculate this, we will get 3.33 radians per second. So here omega RS, that is the omega angular velocity of R with respect to S. And here the direction of velocity is shown. So if I take S as a center and move the compass in the direction for this velocity, so this is the direction. So here also I will locate the direction, that is here this is the direction. So if we observe, this is the direction is the clockwise direction about S. So how we can write the answer? We have to write clockwise about S. So these two calculations are getting completed. Now we will move for the acceleration diagram. But before that, we have to understand that for acceleration there are two components, that is the radial component of acceleration and tangential component of acceleration. So suppose if we consider xy is the link, then how we can calculate the radial component of acceleration? So we have to show here a raised to r xy is equal to linear velocity square for this link xy divided by length of link xy. And this radial component is in the direction parallel to the link. Now the next is tangential component. So for this tangential component, here we have to indicate us, that is a raised to t xy is equal to alpha, that is the angular acceleration alpha xy multiplied by the length of link xy, and it is in the perpendicular direction to the link. So from this we can say that the radial component and tangential components are perpendicular to each other. So if we observe, we know what is the linear velocities for these links. So from this linear velocity we can calculate the radial components. So So first we will take the link QP. So P is the fixed point and this Q is rotating in clockwise direction about this point P. So if we consider its crank, then it is getting rotated at constant motion. So this constant motion, or we can say constant revolution, there is tangential component becomes 0. Or simply we can say that when for any rotational motion, suppose this angular acceleration is not mentioned, then we have to take the tangential component for this crank is equal to 0. So here is also in this question the alpha is not mentioned. So we are going to consider only radial component for this crank PQ. So how to calculate the radial component? By using this formula, a raised to r qp is equal to v square qp by qp. So vqp is 0.625. So 0.625 square divided by 0.062. Now this length we have to take in meter. So answer is 6.3 meter per second square. So now for this link QR and RS also we have linear velocities that we have calculated. So from this we can calculate the radial component of RQ, that is V square RQ by RQ, that is equal to 0.35 square divided by 0.175, which is equal to 0.7 meter per second square. And then a raised to r rs, that is the radial component of rs, V square rs by rs. So rs is having 0.375 meter per second linear velocity. So 0.375 square divided by 0.1125, which is equal to 1.25 meter per second square. So these are the radial components. So for this crank PQ, we are considering this a raised to r QP, or simply we can say AQ. That is the acceleration of this Q with respect to P, that is AQP. Because here a raised to T QP we will consider it as a 0. Now we will move to draw the acceleration diagram with some suitable scale. So here I will use scale for 1 meter per second square is equal to 4 centimeter. And I will use the red marker for the radial component of acceleration and tangential component of acceleration. Now if we observe the diagram, here point P and S are the fixed points. So I will select here one particular point and I will show here for acceleration diagram as a P dash and S dash. Now if we observe, here is the crank PQ. Now for this crank we are going to consider only radial component. There is no any tangential component. So we know that the radial component is parallel to the link. Now the main question is that about the direction. So for which direction we have to select? So if we observe here, the crank is getting rotated about point P. So we have to show arrow towards the fixed point. So I will show here the arrow. So this is the arrow for the radial component. So now I will take the line parallel to this link PQ but in the downward direction. So I will use the black marker because here a raised to r QP, that is nothing but AQP, that is the acceleration of QP. So we will consider here this is as a total acceleration. Now what about the scale? So with this scale, for 1 meter per second square 4 centimeters. So here a raised to r QP is 6.3 meter per second square. So 6.3 multiplied by 4, that is 25.2 centimeters. That scale we have to use. So I will take the line parallel to this PQ and I will transfer this to the acceleration diagram. Now we will use here, this is the end point, that is this is the point Q dash. So I will use the direction also. Initial point is P dash, final point is Q dash. This is the direction. So for this direction I will use AQP, that is the acceleration of Q with respect to P. Now we will move for the next. So again there is the next link is RQ, that is initial point is here. If we observe the point in between this point, 2 points, that is Q and R, here is the point Q dash. So now the dimension for this radial component that we have to measure. So for this radial component, that is a raised to r cube 0.7 meter per second square. So for this we will use this scale. How many centimeters that we have to take? That is for 1 meter per second square 4 centimeter. So for here 0.7 meter per second square, it is 2.8 centimeter. That is 0.7 multiplied by 4. So we have to take this scale 2.8 centimeter, and we have to take, or we have to select the direction parallel to this QR and passing through Q. So how to select the direction for this radial component? So this is important point, and remember that for radial component I will use here the red marker. So if I take the line parallel to this, now draw here one line in the form of dash. I will draw currently on both the sides because we don't know which direction we have to select. So whether the right hand side or left hand side, that we have to select. So if we observe here, the notation is that a raised to r cube, that is the acceleration of r about q. So here we are taking velocity also, velocity of r about q. That means I will take the direction towards the center, that is about q means I will take towards this. So we have to take the same direction, that is towards the left hand side. So I will use here the direction towards the left hand side and scale 2.8 centimeters. So I have to take here scale 2.8 centimeters. So here is the direction. So from a dash I will select here as a double dash, and this vector a dash to a double dash indicates us the a raised to r cube. So I will write here a raised to r cube. Now tangential component. So we know that the radial component and tangential component are perpendicular to each other. So how to select? So if I draw perpendicular line passing through this a double dash on both the sides but perpendicular to it. So if I take here one line and in the form of dash I will draw this tangential component. So if I take in the downward direction also, now how to select the direction for this tangential component? So for that we have to take, or we have to observe this link RQ. Now velocity is in the upward direction, so we have to take in the same direction for the tangential component. So I will take here same direction, that is the upward direction. Now the magnitude for this tangential component is not known, but I can show here direction also, and what we can show that is this is the tangential component of RQ. So I will write here a raised to t RQ. Now the magnitude is not known. Now in the same way we will move for the link RS. So here is the fixed point S. So if we observe here again, we have to find out the radial component. So here scale for the radial component. So here a raised to r RS, that we have calculated earlier, that is 1.25 meter per second square. So with this scale, that is 1.25 multiplied by 4, that is equal to 5 centimeter scale we have to take. Now what about the direction? Because we know that one point in between R and S, point S dash is present here. So I have to take the line parallel to this RS. So if I take the line parallel to this RS and passing through this point S dash, so I will currently take here, this is the radial component on both the sides of S dash. Now how to select the direction? So again we will observe here. Now if we observe, here is the VRS, that is the velocity of R with respect to point S. So here S is the center. So we have to show arrow, that is the direction of arrow towards the center. So if I show this, that is the arrow, that is it is in the downward direction. So in the same way I have to show here, that is the radial component in downward direction, and what is the scale, that is 5 centimeters. So I will take here the distance of 5 centimeter and I will show here arrow, and this is the radial component, that is a raised to r RS, and here is the point from S dash I will take S double dash. Now we will move for the tangential component for this link RS. So here we have to take one perpendicular line. So here this VRS indicates the perpendicular line because we know that the linear velocity is perpendicular to this link RS. So I will take here the line parallel to this velocity and I will draw one horizontal line passing through this point S double dash. So if I draw this line on both the sides, then what is happening here? So on this side there is no any link available, but on the left hand side here there is the intersection for this Q double dash to R dash. So this point of intersection we will say R dash. So I have to show arrow from S double dash to R dash. So here is the arrow and I will show what this vector S double dash to R dash indicates, that is the tangential component, that is A raised to T RS. So we can say that for this tangential component we have to take the velocity is in the opposite direction. So I will take here that this is the tangential component. So I will show here the tangential component but in the opposite direction. Now how we can find out the total acceleration? So endpoints of this radial acceleration and tangential acceleration that we have to join. So here is the A dash and R dash. So I will join this. Now here is also S dash and R dash. So I will join this. So for this S dash R dash, the velocity is in the opposite direction, that we can say. Now this is the acceleration diagram. Now we will move for the calculation. Now what is the question here? That means we have to find out the angular acceleration for this link QR as well as link RS. So for these two links we have to find out the value of alpha. So if we observe for this value of alpha, we have to find out the tangential component. That is the tangential component for these two links by using this formula. So alpha of any link, we can say that tangential component of acceleration divided by the length of the link. So how to find out? So here is the tangential component of RS is given and here is the tangential component of RQ is given. So for this tangential component of RQ, so I will say A raised to T RQ is equal to, we have to measure R dash Q double dash. So if we measure, we will get length 15.4. So this 15.4 centimeters. So here if I write 15.4 centimeters, then here is the question mark. So 15.4 multiplied by 1 divided by 4, that is equal to 3.85 meters per second square. Then in the same way A raised to T, here is A raised to T RS. So for that I have to measure this tangential component. So if I measure this, I will get 18.4 centimeter. So again I will use the same scale and I will get here 4.6 meter per second square. So from this tangential component I can calculate the value of alpha. So alpha of link QR. So here is the link QR. So A raised to T RQ divided by length of the link QR. That is 3.85 divided by 0.175. Because this length we have to take in meters. So which is equal to 22 radians per second square. Now main important thing is that how to decide its a direction, because we have to write the direction also. So here A raised alpha QR, that is alpha of this Q with this alpha for this Q about the center R. So if we observe, the radial component is in the downward direction, that is the radial component is from point R towards Q. So we have to take R as a center and the tangential component is in the upward direction. So if I take R as a center and if I move the compass in the direction, then I will get here the clockwise direction. So I can say that here is the clockwise direction about R. Clockwise about R. So this R we can, it is important because here R we have taken as a center. So we can also write answer, that is in anti-clockwise direction about Q. Or we can say that anti-clockwise about Q. Now in the same way here, if we observe radial component is in the downward direction and tangential component is towards the left hand side. So if I take R as a center and move the compass in the direction, I will get this. So again we can say clockwise. So clockwise about R. But we can say if we take S as a center, then we can say that anti-clockwise about S. So we can use here any one of the answer in between clockwise or anti-clockwise. So here is the answer.